This is the video over the AP exam questions for our Chapter 10 test. And let's begin with a multiple choice question. There's only one of these. We have an equation, a general equation. Gas W plus gas X gives you gas Y and gas Z. If gases W and X react in a closed rigid vessel to form Y and Z, the initial pressure of W is 120 and that of X is 160. No Y or Z is initially present, which means we just have our reactants, no products. The experiment is carried out at constant temperature. What is the partial pressure of Z when the partial pressure of W has decreased to 1.0 atm? Now this is really a simple stoichiometry problem in which we use the coefficients in front of here, which is a 1 to 1 to 1. Instead of using moles, we can use atmospheres, we can use pressure. Recall that moles and pressure are directly related. As moles goes up, pressure goes up, which means if we lose moles, we lose pressure, exactly a proportionate amount, which simply means we can actually use these numbers to stand for pressure. You can also use them to stand for volume, for pressure, because both volume and pressure are directly related to moles. This means directly related. So what we're saying is that we begin with 120 of W. So in front of here, let's clean it up a bit. This is 120. And then it's saying that at the end of the reaction, W has decreased to 1.0. So we began with 120, and we got down to 1.0, which means we lost 0.20. 0.20, you can say moles, or 0.20 atmospheres of W was lost. Now for every 1 W that gets lost, let's see, they're asking for Z, 1 Z gets formed. So we actually lost 0.20 of W, we would gain 0.20 of Z. And it's really as simple as that. They're really testing you to see whether you understand that moles and pressures can be treated the same in a stoichiometry problem. So the answer is as easy as 0.20 atmospheres. Okay, the next one is a bit more involved, so let's get at it. We have a 5-gram sample of a dry mixture of potassium hydroxide, potassium carbonate, potassium chloride. These, by the way, are K2OH hydroxide. Carbonate is K2. Let's try that again. It's just KOH. Potassium hydroxide, K2CO3, and then KCl. It's reacted with 0.1 liter of 2 molar HCl, the acid. Now, whenever you react each one of these with an acid, it'll be for HCl versus KOH, you'll get a neutralization reaction. For the other one, you also get a neutralization reaction for K2CO3, but it'll produce a gas. For KCl, you won't get any reaction. So really, the only reaction that we care about that will produce a gas, this is a gas type question, will be between HCl and K2CO3. Again, because HCl and KOH, it's an acid-base neutralization, you get salt and water. But with K2CO3, you actually produce a gas. Which gas? You will produce CO2 gas. So this is the compound that we'll be focusing on. And this is something you have to kind of figure out or know before continuing with the problem. So let's write that equation. We have HCl plus potassium carbonate. Now this is also a double replacement reaction, so this allows us to use some double replacement. Hydrogen and potassium swap places. What we get ourselves is we get technically KCl plus some H2CO3. Now you don't see any carbon dioxide gas formed yet, but H2CO3 actually breaks down into H2O and CO2. And these are the two products. So really, this is a little bit of a detail that you may not have known, but anytime you have a carbonate reacting with an acid, you get yourself carbon dioxide gas produced. So now make sure we balance the equation so we can use it properly. And the balanced equation, we have 2 potassiums, and let's see, we've got 2 chlorines. How about a 2 in front of here? And that should do it. Our oxygens are 3, so we have 3 on the right. Okay, now we can go on with the problem. A 249 milliliter sample of dry CO2 gas measured at a temperature and a pressure is obtained from the reaction. What's the percentage of potassium carbonate in the mixture? So in this case, what we'll do is to find out the percentage of carbonate in the mixture, we have to know essentially how much carbonate, potassium carbonate, was formed. And that we can get from the stoichiometry of CO2. Because we're measuring these quantities are for the gas, CO2, we can then go from CO2 back to K2CO3 and find out what the percentage is. So let's go ahead and apply PV and RT to find out how many moles of CO2 we actually formed. And remember, moles with PV and RT is PV over RT. Our pressure in this case is 740. We'll just convert that on the spot to atmospheres. Remember, every pressure must be in atmospheres because R is defined in atmospheres. So we get 760, that's what we're doing here. Our volume is 249. Because our R is defined in liters, we must put this as 0.249 liters. The R is a constant, 821. And the temperature looks like 22. That gives us 295 Kelvin. Okay, if you calculate this, if you plug this into your calculator, you should get a fine value of 0.0100 moles of CO2. Now, because the stoichiometry tells us it's a 1-to-1 mole ratio, that will be actually the same as our K2CO3. So you don't have to convert. You just say, well, we have 0.0100 moles of potassium carbonate. Now, in order to get the percentage of potassium carbonate, we'll have to convert this into grams. So let's do that, and then we'll apply and we'll just get the percent. So we got ourselves 0.0100 moles of potassium carbonate. A mole of potassium carbonate, if you add up the molar mass, grams of K2CO3, would get you, if you do this properly, should get you 138.21. Verify that. And that, if we do this calculation, we should get ourselves 1.38 grams. Now, they're asking for the percentage of potassium carbonate. So we have grams of K2CO3 potassium carbonate. We've been told that our total mass is 5, so we're really asking what's the percentage of 1.38 of 5 grams. So if you get the percent, you got 1.38 over 5 grams times 100 because it's percent, and you get yourself a fine value of 27.6%. And this is the percentage. Now, I should say one quick thing before we finish. They gave us some information about HCl here, and we didn't really use it much. And you may have said, wait a minute, don't we have to use those numbers? Well, it turns out we're adding this HCl in excess. And we're doing that to make sure everything else reacts completely. So this won't mess us up because, in fact, if you calculate, if you were to get the how many moles we have here, this is molarity, right? Molarity is moles over liters, which means moles is molarity times liters. If we multiply these two numbers, you get yourself 0.100 times 2.0. I know this is a bit thin. You get 0.2 moles of HCl. Notice we formed 0.01 moles of CO2, or we formed rather 0.01 moles of K2CO3. So we have much less of this guy than we have HCl. We have an excess amount of HCl, way too much HCl. HCl is in excess. It will not be the one that limits us. That's why we essentially kind of ignored it. Okay, so I'll put a second video over number 3. Number 3 is even more exciting, as you might suspect. So this completes for us the first 2 questions.